So in this video, we're going to continue to talk about improper integrals, and we'll basically say that there's a different type of improper integral that's a little bit different from the ones that we saw in the past couple of videos. So in the previous videos, we looked at integrals, we saw integrals that were of a form where one or both of the bounds were either positive or negative infinity. So, that might have looked like the integral from a to infinity, the integral from negative infinity to b, dx. And then we also saw integrals of the form negative infinity to infinity. And so, what made these integrals different from integrals we've been working on earlier in the class was that because the bounds are infinity or negative infinity and not just a number, you can't directly apply the fundamental theorem of calculus. You have to use limits. And so these type of integrals that I just wrote down, these are called type 1 improper integrals. So just to give a quick example on this picture here, if we had the integral from 1 to infinity, so this function, by the way, that I have graphed here is 1 over x squared. So we actually already did this example, the integral from 1 to infinity of 1 over x squared dx. And that one turned out to converge, right? I think it came out to be 1/2. But the area you would be talking about if you were evaluating that integral would be the area that starts at 1 and then that keeps extending this way. So it's an infinite region. It goes on forever, but it has a finite area. So I'll just write this one converges. And if you want to remember how that works, you can go back. That was like the first example we did in the first video. So in this video, we're going to be focusing on a different type of improper integral. So I'm going to first write down what that integral is, and then we'll talk about, what makes this an improper integral. So let's say that now we were doing the integral from 0 to 2 of this same function. So there's no infinity in the bounds, right? Like there's 0 and they're 2. They seem like they should be fine. But let's look at the picture. So if I were to shade in the region that corresponds to this integral, just like the green one, it contains actually an infinite region, and it's infinite in a different way. So the green region, the one that was the integral from 1 to infinity, that was infinite because it kept going on and on and on out to the right. This one is infinite because it has an infinite height, right? Because the function 1 over x squared has a vertical asymptote at x is equal to 0. And so this graph is never actually going to touch the y-axis. And so what that means is that if we were to, shade in this region that I did in purple, you would be shading forever. It keeps going and going and going. The graph is never going to cross the y-axis. And so this is an infinite region. And so even though the bounds are not infinity or negative infinity, it still kind of has something in common with the examples we were doing in the past couple of videos. It's still this infinite region, and so it's still called an improper integral. So let me kind of summarize what these improper integrals we'll be looking at today look like. So in this video, we'll see integrals of the form just integral from a to b. So that part is not really what the issue is. The issue is that your function has an infinite discontinuity. So an infinite discontinuity just means a vertical asymptote. So I'll write that down below. An infinite discontinuity at either x is equal to a, x is equal to b, so at one of the bounds. So in this case, it would be the lower bound, right? We have an infinite discontinuity at x is equal to 0. But we'll see that there's also cases that where it might have an infinite discontinuity not at one of your bounds, but somewhere between them. So we'll say also, or at x is equal to c, where c is some number between a and b. So this is also what's called an improper integral. So if you have an integral where there's a discontinuity either at one of your bounds or somewhere between the two bounds, then this is what's called a type 2 improper integral. So it's not improper because it has, infinity or negative infinity as its bounds, but it still kind of has an infinite sense to it, right? Because of the fact that it has a vertical asymptote, you still have this infinite region. So we're going to do this first example here in just a moment. One thing I want to point out though is if you had to guess, looking at this picture, would you guess that this one is going to converge or diverge? So personally, just by kind of comparing what's going on with the one in green with the one that's in purple, the one that's in green really kind of gets close to the x-axis very quickly. So even though it extends infinitely, it's very, very thin as you extend out towards higher x values. Now this one, it's a different kind of shape. It has a vertical asymptote, but notice that the graph doesn't really get close to the y-axis very quickly. It kind of takes its time in getting closer and closer to the y-axis. And so just visually, you can see that this stuff we shaded in purple, it looks a lot bigger than what we shaded in green. And so what we'll see is that this one diverges, and we'll actually work that out in a second. Okay, so let's actually do this as an example. So we're going to do the integral from 0 to 2 of 1 over x squared dx. So how is this going to work? Well, it's basically very, very, very similar in the setup to how we did the other type. So what do? We focus on what is the kind of problematic bound. In this case, it's 0, right? That's one of the bounds that gives us an issue. The function is undefined. It has a vertical asymptote at x is equal to 0. Nothing's wrong at x is equal to 2. And so whatever that bound is, that is kind of your problematic bound, that one you're going to change it to a t. So we're going to rewrite this as the limit, now not as t approaches infinity, but as t approaches 0, of the integral from t to 2 of 1 over x squared. So there's one more thing we should add in here just to be kind of technically correct. So when we're doing our limit, in general on these, you're going to need to put in whether it's from the left or from the right. It's not going to actually impact your final answer, but it will impact something along the way. So if we look at our picture and we think about, okay, we're taking the integral from 0 to 2, well, that means that we're approaching from the right? Like we're looking at it just doesn't make sense to take the limit from the left because we're not looking at values that are to the left of 0. We're, if you imagine like taking different values of t, you can almost think of t as being like a slider, right? So you could put t here, for example, and you could put t here, and you could put it here and here, and you could get closer and closer to 0 as you take your limit, but you wouldn't actually ever go to the left of 0. So the limit is from the right. So this is the limit as t approaches 0 from the right. And now we just do this the same as we did in the last video. So we just focus on evaluating the integral, and then once we have the integral and the antiderivative, then we take the limit at the end. So this is going to be equal to the limit as t approaches 0 from the right of, so our antiderivative in this case, so here we have x to the negative 2. Right, that's 1 over x squared. So the antiderivative is negative 1 over x, right? Because that's negative x to the negative 1. If you take the derivative of negative x to the negative 1, you get positive 1 over x squared. And we're evaluating this at 2 and at t. Okay, so this is going to give us the limit as t approaches 0 from the right of negative 1 over 2 minus negative, so it'll become plus 1 over t. So the 1/2 does not have a t in it, right? So that's not going to be affected by the limit. But the second part does, right? 1 over t. And so what happens as you bring t closer and closer to 0 while staying to the right of 0? Well, 1 over t will go to positive infinity, right? Just think about plugging in like 0.1 or 0.01 or 0.001. You're going to get results that get higher and higher and higher. And so this part goes to infinity, and then the 1/2 just isn't really going to affect it. So your final answer would just be infinity. However, just like with the improper integrals in the last few videos, we don't care whether it goes to positive or negative infinity. We just say, okay, it diverges. So if it diverges, generally speaking, at least in this class, we're not going to worry about where it diverges to. You just say it diverges. And so that's the reason that this plus doesn't actually really matter, because the plus is the reason that we get positive infinity instead of negative infinity, but either way it diverges. So you don't have to worry too much about whether you're going from the left or the right, but if you want to kind of be technically correct when you do these, then you do want to put that in. So before we do our next example, I just want to kind of refresh your memory on a couple of things for limits that you're going to want to know. So we're not going to have too many different situations that come up with limits in this context. There's really two main ones that you want to know. So limits you should know. So the first one is basically limits that look kind of like what we just did. So if you have a limit, and it doesn't matter whether it's approaching 0 or whatever it's approaching, but if you have the limit as t approaches some number of some function of t, if that limit is equal to 0, then the limit as t approaches a of 1 over f of t is either equal to positive or negative infinity. It depends on what the function is, what you're approaching, whether you're approaching from the left or the right. But this is basically the situation we saw. So we had a denominator that was going to 0 and a numerator that was just 1. And so in this case, we got positive infinity, but if, for example, this was -1 or this was negative t, or if we were approaching from the left instead of the right, then we would get negative infinity. But regardless, anytime you're dividing 1 by a very, very close to 0 number, regardless of whether it's positive or negative, you're going to get a result that's either very, very large positive number or very, very small negative number. Okay, so other fact that you should know is, and this is one of the ones that we actually talked about the other day. So ln of x is going to come up. And the reason it's going to come up is basically, it's a pretty common antiderivative to get, right? If you have like 1 over x, the antiderivative is ln of absolute value of x. So ln of x comes up. So what does the graph of ln of x look like? Well, it looks like this. So this is f of x. I'll do t since that's really the variable we'll be focusing on. So if you have f of t is equal to ln of t, so the limit as t approaches 0 from the right, and it has to be from the right because ln of x isn't defined on the other side. And we won't really have to worry about that too much though, because we're always taking the absolute value. I'll show you what I mean by that in probably actually the next example. But anyway, the limit as t approaches 0 from the right of ln of t is going to equal negative infinity. So that's another one that will definitely come up. There might be a couple others, but I really think that these are the main two that you're going to want to be familiar with. And again, as soon as you get either positive or negative infinity, you just say it diverges. Okay, so let's look, actually, before we look at this, let me just show you where I kind of wrote down some general facts here. So this says if your function is continuous on the interval from a to b, so remember this is interval notation where this bracket means a is included, this parenthesis means b is not included. So if you have a function that's basically continuous everywhere on your interval from a to b except for at b, then you can do what we just did in the last example, right? You can take a limit. Really, the example that we just did actually looked more like this one because the discontinuity was at our lower bound. But either way, it's pretty much the exact same setup. So you're just kind of replacing whichever bound is your problematic one. You're replacing that with t, and you're taking the limit as t approaches whatever that problematic bound is. And this just says discontinuous, but really in this class anyway, the examples we'll be focusing on are going to be ones with infinite discontinuities. We'll see an example at the end with a removable discontinuity. Technically, these statements are also true for removable discontinuities, but you basically don't have to use limits with removable discontinuities. But don't worry too much about that. This video is really focused more on integrals that have infinite discontinuities in them, so vertical asymptotes. And then we'll get to this third point at the bottom after we do a couple more examples. Okay, so this example here is the graph of, so this is f of x is equal to 1 over the square root of x minus 3. So one thing that's going to be important in this section is, I gave you the graph, but without having the graph, you should be able to tell, where does your function have a vertical asymptote. So this function has a vertical asymptote at 3 because if you try to plug in 3 to this function, you would get 0 in the denominator. So anytime you have 0 in the denominator, especially without having 0 also in the numerator, so like just 1 divided by 0 basically, that means that you have a vertical asymptote. So in this case, we want to do the integral from 3 to 5 of this function. So again, our problematic number in this case is also the lower bound. So let's make that, we're going to turn that into our t and into our limit. So we're going to be taking the limit as t approaches 3. And this time, again, we're approaching actually from the right. So, what's the area we're looking at here? We're looking at this region. And, I can't possibly draw the whole region, but even though it kind of looks like the graph touches the line x is equal to 3, it actually doesn't. It's a vertical asymptote, so it never actually touches x equals 3 because the function's not even defined at 3, right? So it can't have a value of x is equal to 3 because it's not defined there. So the graph never touches x equals 3. But we're approaching from the right, right? Because we're looking at values that are to the right of 3. And so now we're doing the integral from t to 5 of 1 over the square root of x minus 3. So now we want to focus on the integral. And so in this case, this is one where it's a pretty simple substitution, and it's one that it might be convenient for you to be able to recognize without having to explicitly write it out. But just in case you're not there yet, let's actually do this integral without the bounds. Let's first just figure out what the antiderivative is, and then we'll come back to the bounds. And I think in general, for improper integrals, that's usually a better approach, is to first just find your antiderivative, because otherwise when you change the bounds, then that's also going to force you to change what you're limiting. So I think there's just like more confusion that can arise there. And it's better to just focus on it as an improper integral. And then you don't have to worry about, doing a substitution, changing the bounds, stuff like that. Okay, so if we have the integral from, or the indefinite integral of 1 over the square root of x minus 3, what's the substitution you can do? Well, you can let u equal x minus 3. So why does that work? Well, because du would just be equal to dx. And so this is one of those substitutions where you can just kind of put it in without having to worry about kind of canceling anything out, because we're just going to replace this with 1 over square root of u du. And then what is the antiderivative of this? Well, 1 over square root of u is u to the negative 1/2. And so the antiderivative is going to be 2 times u to the positive 1/2. And then we just want to put back in what our original variable was so that we don't have to change the bounds. And so that was x minus 3. So this is basically, it's kind of like the examples that we did with what I call partial fractions, where, if you take the antiderivative of like 1 over x minus 1, you don't really have to do the substitution. You can just say, okay, that's going to be ln of absolute value of x minus 1. Same kind of idea here. You can basically just treat this as though it's just 1 over square root of x, except for that instead of x, you have an x minus 3. And that's just because there's no coefficient on x. There's nothing that kind of would come out from the chain rule that would mess with the derivative, and so the antiderivative is fairly straightforward. Okay, so now that we have our antiderivative, we can go back to our limit. So we have the limit as t approaches 3 from the right so we found our antiderivative to be 2 times x minus 3 to the 1/2, and we're evaluating that at 5 and at t. Let me actually scooch that down. I think I put it a little bit too high. So that's going to be the limit as t approaches 3 from the right. So the first one will plug in 5, and we end up with 2 times 5 minus 3 is 2 to the 1/2 minus 2 times t minus 3 to the 1/2. So the first part is just going to be 2 root 2, right? There's no t in there, and 2 to the 1/2 is just square root of 2. So we're going to get 2 root 2 for the first part. And then what about for the second part? Well, let's think about what happens when you plug in a number that is close to 3 and just above 3. So like 3.1 or 3.01. So when you plug in numbers that are really close to 3, then you would get something that's really close to 0. And so and specifically here, right? This, if you do t minus 3, that's going to give you something that's really close to 0. And so you're going to end up just with negative 2 times the square root of 0. And so that's just 0. So you just end up with 2 times the square root of 2. So this one converges. And when they converge, you do want to say, what they converge to. Whereas diverges, you just say, okay, it just diverges. So what's different about this one? I mean, the main thing that's different is when we took the antiderivative, t was in the numerator, not the denominator, right? Or there was no denominator. But when we plugged in t, or if we took the limit of t, we got 0, but that 0 was not in the denominator. Whereas in the last example, we're letting t approach 0, but that 0 was in the denominator, and that's what caused the issue. So it basically has to do with, after you take the antiderivative, is the part that you're going to take the limit of, is it in a denominator, which will kind of force things to go to infinity or negative infinity, or is it just kind of a number on its own? But, that's not really a rule you have to memorize. You just have to kind of go through the process and see what you get for your limit at the end of the day. One other thing I just want to point out is that notice that this region in purple, it really looks like a more kind of small region than this one in purple, right? This was the one that diverged, and it was because the vertical asymptote was such that the graph just didn't really get there very quickly, right? It eventually will get close, but it's just kind of taking its time. Whereas in this one, you can see that very, very quickly, the graph gets very close to the vertical asymptote. So that's why this one converges. Okay, so we're going to look at another example. So this is going to be one that I kind of think it's a little trickier because it's kind of a hidden improper integral. So this is the function f of x is equal to 1 over x minus 1. So we can see from the graph, or you could tell just by looking at the function, that this has a vertical discontinuity or a vertical asymptote at x is equal to 1. And so the integral I want to do is the integral from 0 to 2 of 1 over x minus 1. So what do I mean when I say this one's kind of hidden or tricky? Well, notice that the discontinuity is at 1, but 1 is not one of your bounds. So it would be very easy, I think, to overlook, we have the graph right here, but let's say I just handed this to you on a test. Chances are you wouldn't check, whether your function had a discontinuity in the middle of your bounds. So that's something that you're going to need to check from here on out, is if the function you're integrating has some kind of a vertical asymptote or infinite discontinuity, you need to check whether that discontinuity happens within your integral. So because 1 falls between 0 and 2, this is still an improper integral, even though that 1 is not one of our bounds. So how do we deal with this one? We actually just split it up, because really the only improper integral, that we know how to do is if the discontinuity is at one of our two bounds. And so that's what we basically just force to happen. So how do we do that? Well, we just split this up and say it's the integral from 0 to 1 of 1 over x minus 1 plus the integral from 1 to 2 of 1 over x minus 1, right? Because now both of these are integrals where there's a discontinuity at one of the bounds. So let me just also shade the region we're referring to here. So the first part would be from 0 to 1, so that's this region here. And then the second region is from 1 to 2. Oh, that's not to 2. 1 to 2, so it ends here. Okay, so let's start with the first one. So for the first one, this is going to be the limit as t approaches 1. And in this case, we're actually approaching 1 from the left, right? Because if you imagine, kind of sliding the upper bound, you start at 0 and you can't go any further than 1. So you're going to be approaching 1 from the left. And now we're doing the integral from 0 to t of 1 over x minus 1. And just like with the other improper integrals, when you split it into 2, just focus on one of them at a time. Because if one of them diverges, the whole thing will diverge. So there's no point in kind of wasting your time evaluating both of them at once. Take them one at a time. So what do we get for our antiderivative here? Well, the antiderivative of 1 over x minus 1 is ln of absolute value of x minus 1. So this is the limit as t approaches 1 from the left of ln of absolute value of x minus 1. And we're evaluating that at t and at 0. So in this case, we can actually see why the absolute value is important. So when we plug in t, we get I still need the limit as t approaches 1 from the left. So when we plug in t, we get ln of absolute value of t minus 1. And then when we plug in 0, we get ln of absolute value of 0 minus 1. And so that's going to be ln of absolute value of -1. If we didn't have the absolute value, that would actually be undefined. You can't take ln of a negative number. And so that's why the absolute value bars are important. They force the antiderivative to be defined at all values of x. Okay, so what about the limit as t approaches -1 of ln of t minus 1? Or sorry, not -1, 1 from the left. So what happens when you plug in numbers that are really, really close to 1 for t? Well, you're going to get ln of basically 0, right? You're going to get ln of numbers that are really close to 0. And so we already talked about earlier that if you look at the limit as t approaches 0 of ln of t, that's -infinity. And that's basically the exact situation we're in, even though our function doesn't look exactly like this. That's really what we're doing, because if we plug in 1, you're going to get 0 inside of your logarithm. So taking the limit as t approaches 1 of ln of t minus 1 is the same as taking the limit as t approaches 0 of just ln of t. You have the same overall effect of getting 0 inside the logarithm. And so that part is going to be -infinity. This next part would be ln of 1, which is 0, but we don't really even care about that, because as soon as we get -infinity, that tells us that it diverges. And we don't have to do the other one. The whole thing diverges. If you were to do the other one, you would actually get positive infinity, which maybe isn't too surprising. If you look at the graph, it's very symmetric and the regions kind of look like they're the same amount of area. But it would not be correct to add together negative and positive infinity and say it equals 0. Even though maybe you look at the picture and it looks like they should cancel each other out, even though that in some sense, maybe that makes sense, if you're adding up infinite regions, you just can't, infinite regions can't cancel each other out. So we just say it diverges. We don't worry about the second integral. So that's written down here. So it says that if your function is continuous basically everywhere except for at c, but it has a discontinuity at c, then you can break it into two integrals where you force one of the endpoints to be c on each of them, and then you turn it into a limit. And then I should add a note here that says that this is only true if both converge. So if one of them diverges, it just doesn't even make sense to add them up. So you just say, okay, it diverges. Okay, so I want to do a couple more examples. I can't remember if it's on this page. Yes, okay. So this one's going to be a slightly more involved example, but it's really in a lot of ways similar to the one that we just did. So this is the function f of x is equal to 1 over x squared minus 5x plus 6. And what are we doing the integral of? We're taking the integral from 0 to 5 of this function. So how would we figure out, where this function is discontinuous? Well, in the other ones, we could just tell by looking at it quickly, right? Like this one, it's like, oh, x minus 1, it's discontinuous at 1. If your denominator is more complicated, you may have to factor. So this is going to be discontinuous when the denominator equals 0. So when x squared minus 5x plus 6 is equal to 0, and then we can factor this. So x minus 2, x minus 3. And so that's going to tell us this is discontinuous at x is equal to 2 and at x is equal to 3, which we can tell from our picture, but again, in case you didn't have the picture on hand. So what is the region we're looking at here, by the way? We're doing the integral from 0 to 5. So really it's like we're looking at this area plus this area plus this area. I know it's a little confusing, I think, in this picture. But yeah, it's basically, we have multiple infinite issues, right? We have infinite issues going on here, and then we also have them even down here and down here. So a lot more going on in this example than the previous ones. Okay, so how do we deal with this? Well, we have not just one, but actually two different discontinuities within our bounds. And so what we need to do is start by splitting this up into, we'll see that this splits into 3 integrals. So we're going to rewrite this as the integral from, so we can start by saying 0 to 2, right? Looking at our picture, that's the first place that we have an issue. So let's say the integral from 0 to 2 of our function plus, and then the next one would be the integral from 2 to 3. And then the last one would be the integral from 3 to 5. I'm probably getting a little off screen, so I'll scroll over. So why did it have to break into 3 integrals? Well, basically just because we had 2 discontinuities. So we're basically forcing a break in the integral every time we encounter a discontinuity. So we hit one at 2, we have to split it up. Then we hit another one at 3, we have to split it again. Then we hit another, and then that's it. Then the last one is just from 3 to 5. So you might notice that this middle integral actually has both of the bounds are issues, right? They're both discontinuities. So there is a way to do that all in one. You could do that by basically you would use a different variable you'd make like one of them t and maybe the other one u or something like that and take 2 limits. But that's probably not something you've really done before, taking like multiple limits. So another way that you could deal with this is you could actually split it up again. So you could take this integral and split it into an integral from 2 to 2.5 and then 2.5 to 3, for example. So let's just write that out. And we'll see that actually, well, I'm not going to spoil it. We'll see what happens. But yeah, I wouldn't really worry too much about that. You're not really going to, I don't think, in this class run into too many situations like this. This is kind of a, I picked this example to be a little more complicated than most of the ones that we'll see. But yeah, so I'm basically just kind of forcing another break in here. And the reason I'm doing that is because that way all of the integrals that we're evaluating will look like the ones that we've done so far, right? All the ones we've done so far have had one of the bounds have been a number that's okay, and then the other bound has been a number that is not okay. And so now all of them look like that. Okay, so let me just write this last one down and then we're good. Okay, so just like with the other ones, we really only have to go through, or we really just want to start by doing one of them, because as soon as one of them diverges, the whole thing diverges. That being said, how do we find the antiderivative for this function? We actually have to use partial fractions. So this is another one where I think it kind of makes sense to forget about the bounds for a moment and just kind of go aside and find the antiderivative first, and then we'll bring that back in. So what is the antiderivative in this case? Or what's the method for the antiderivative? We want to use partial fractions. So we want to rewrite x squared minus 5x plus 6. We want to rewrite that as x minus 3 times x minus 2, or I'll write it x minus 2 times x minus 3. And then if you remember, how does partial fractions work? We're basically going to imagine that this fraction came from adding together two fractions, one with a in the numerator and one with b in the numerator. And so the first fraction we multiply by x minus 3 over x minus 3, and the second one we multiply by x minus 2 over x minus 2. So that gives us, for a new numerator, we'll have ax minus 3a plus bx minus 2b, all divided by our new denominator. Okay, so now we can do this kind of side-by-side comparison where we say that whatever is this numerator, this has to be the same as the numerator we started with, right? So that means that ax minus 3a plus bx minus 2b, that must equal 1. So if we start with our x parts, notice that there is no x on the right-hand side. The original numerator didn't have any x in it. And so that tells us that a plus b have to equal 0. But on the other hand, if we look at the other parts, those have to add up to 1. So we have negative 3a minus 2b equals 1. Okay, so from here we can conclude that a is equal to negative b, and then we can just put that into our second equation, and we have negative 3 times negative b minus 2b is equal to 1. And so that gives us 3b minus 2b is equal to 1. And so that tells us that b is equal to 1. And so that means that a has to be equal to negative 1. Okay, so now let's bring that back, or let's rewrite our integral. So we have the integral of 1 over x squared minus 5x plus 6. And so we now know that we can rewrite this as the integral of, so a was negative 1, so that was negative 1 over x minus 2, and then b was positive 1. Okay, so what's our antiderivative? Well, for the first one, it's negative 1 times ln of absolute value of x minus 2. And then the second one, it's ln of absolute value of x minus 3. So now we can finally go back to our, what we were actually trying to evaluate here. So remember, we had all these different integrals, let's focus on the first one, and we'll see if that one converges, then we keep going, right? If one of them converges, then you do the next one. And if the next one converges, you keep going, you add them all up. But if this first one diverges, then we're good, we're actually done. So what we're doing is we're doing the integral from 0 to 2, so we can rewrite that as the limit as t approaches 2 of 0 to t. So let's write that back down here. So we have the limit as t approaches 2, and in this case, which way are we approaching? Well, we're approaching from the left, right? Because we're looking at 0 to 2, so we're always on the left of 2. And our original integral was 0 to t of 1 over x squared minus 5x plus 6, but we just figured out that that antiderivative is what is written at the top. So we're going to be now taking the limit as t approaches 2 from the left of this whole antiderivative evaluated at our bounds. And so we're evaluating this at t and at 0. Okay, so let's plug in our bounds and then we'll take the limit. So if we plug in t, we're going to get negative ln of absolute value of t minus 2 plus ln of absolute value of t minus 3. And then when we plug in 0, we get plus ln of absolute value of negative 2, and then minus ln of absolute value of negative 3. Okay, so what happens when we take our limit? Well, these ones are all going to be finite numbers, right? ln of 2, ln of 3, this one we would get ln of 1, which is 0. So these parts are all finite numbers when you plug in 2, or when you don't plug in anything. So we don't really have to worry about those. Those are not going to, we don't have to worry about those unless this one is also a finite number. But if we take the limit as t approaches 2 of ln of t minus 2, well, that's back in that same situation from before where it's going to go to negative infinity, right? So this part here, the limit is negative infinity. But then we have an additional negative sign, and so overall our answer will actually be positive infinity. But then again, it doesn't really matter whether it's positive or negative, because as soon as we get either one, we're just like, okay, we're done, it diverges. And lucky for us, because this was going to be a lot of integrals to do, we don't have to do any of the rest of these because we already know that it diverges. Okay, so I want to just show you one more thing, kind of a counterexample. And actually, sorry, I just realized one thing I forgot to do. So let me go back for a second to not this example, but the previous one. So I just want to show you something really quickly, which is that, so I talked about at the beginning how this was kind of a hidden improper integral. So I want to just quickly show you what would happen if you didn't notice that there was a discontinuity. So let's say that you sort of weren't looking for discontinuities. So you had the integral from 0 to 2 of 1 over x minus 1, and you did it without limits. So let's say you just said, okay, the antiderivative is ln of absolute value of x minus 1, and then I'm evaluating that at 2 and at 0. So that's going to give me ln of absolute value of 2 minus 1 minus ln of absolute value of 0 minus 1. So that is ln of 1 minus ln of 1, because they're both absolute value of 1 or negative 1. And so you'd get 0. And that's just not the right answer. That's wrong. The correct answer is that this diverges. So I just want to really point out that if you have a discontinuity that's in the middle of your integral, there's a really good chance you won't actually even notice. If you just go and do the integral using FTC, nothing is going to happen that's weird. You're going to get a normal answer, but that normal answer is just wrong. So just be aware that kind of from here on out, anytime you see an integral, so for example, like on the final exam, I'm not going to announce every time that it's an improper integral. You're going to be expected to do that quick check for yourself. Look at where is the integrand undefined and make sure that that number doesn't fall within the bounds. So by the way, if you were doing the integral, let's say from something else, from let's say like 2 to 3 of 1 over x minus 1, well, that would be fine because the discontinuity doesn't fall between 2 and 3. So it's really just a matter of whether the discontinuity is within the part that your bounds or not. Okay, so one last example, and this is kind of, like I said, kind of a counterexample that I just wanted to point out, which is that if your function has a removable discontinuity, so a removable discontinuity is just a hole. You don't need to actually use limits. So this is one example. So let me just finish writing down this sentence. Okay, so this example here is, so the function is, let's see, it's x minus 1, and we're going to be integrating, by the way, from 0 to 3. So the function is x minus 1 over x squared minus 1. So this one has actually two discontinuities, right? So it has a vertical asymptote at -1, but -1 doesn't fall within our bounds, so we don't need to worry about that. It also has a hole at +1. So how could you tell that that's going to be a hole and not a vertical asymptote if you didn't have the graph? Well, if you take this function and simplify it, so if we have x minus 1 over, and so the denominator would be x plus 1 times x minus 1, well, you could cancel out this x minus 1. And so you would get a new function, which is 1 over x plus 1. So one thing I just want to make clear is that this new function, 1 over x plus 1, it's not technically exactly the same function as what you started with. What this new function would be is the same as the function we have graphed here, but just with the hole filled in. So that's something we talked about in Calculus 1, is that we talked about it in the context of limits, so it was a little different, but we talked about the fact that if you do algebraic simplification, you're not like completely changing your function, but you are changing it just enough to basically get rid of the discontinuity. Now, when you have a vertical asymptote, you're never going to be able to do that. You're not going to be able to simplify that away. But if there's a simplification you can do and it gets rid of a discontinuity, that means that it was not an asymptote, it was a hole. And you basically just don't have to worry about it when you're integrating. Because really this hole is, this is kind of like an exaggeration, the way it's drawn in the picture. Really, it's just like a pinprick. It's like just the tiniest point is taken away. So it just doesn't really affect the value of the integral the same way that a vertical asymptote does. So how would you evaluate this? Well, you could just then, after doing that simplification, you would have 1 over x plus 1. And so you would have ln of absolute value of x plus 1, and you would evaluate it at 3 and at 0. And so you would end up with ln of absolute value of 4 minus ln of absolute value of 1. So ln of 1 is 0, so we would just be left with ln of 4. And that's fine. It would just, that would be your answer. So when you have a hole, basically, if you can simplify your integral or your integrand and get a new function that doesn't have any issues in your bounds, then you're fine. Then you can just evaluate the integral normally. And if you can't simplify away whatever that issue is, well, that means it's a vertical asymptote and you do have to actually use improper integration. All right, so that's it for this video, and we'll be moving on to some new topics in the next few videos. So I will see you then.